Hello, my name is Cole Dumas, and just to start off by saying I did most of my research in the engineering department, so most of my stuff is going to be focused around electrical and computer engineering. To start off, the topic of my poster is understanding the impact of machine learning tasks on power consumption of modern mobile devices. So first off, what is machine learning? Well, it's exactly what it says. It is a machine that is learning. So let's say you have a virtual reality headset. Well, most of those have what's known as object detection. And basically what that means is it can take an image and determine what is closer to you and what is farther away from you. And let you know if you're going to run into it or not. Now let's say you have let's say there's a grayscale image. So if you have darker pixels, they're going to be closer. It's usually what it looks like when you look at it. And more lighter pixels are going to be farther away because there's more light going through. That's not always the case. Because if you have some certain shadows and whatnot, there might be darker pixels that are farther away. So if you have a traditional computing algorithm, it's just going to assume that the darker pixels are closer and the lighter pixels are farther, which leads to inaccuracy. Well, this is where machine learning comes in with this. A machine learning algorithm looks at things in a more human-like way. So it can using specific skills, we are able to manipulate machine learning into understanding certain things and making things such as object detection more accurate. So next up, what is a modern mobile device? Well, what do I mean by that in terms of modern mobile devices? I mean like your smartphones, your cell phones. Those are modern mobile computing devices. And within all of these devices, you have a CPU and a GPU. So we have the CPU and the GPU. This is a big core and a little core. Right now, all we need to know is that this is the CPU. Now, a CPU and a GPU, what they do is they carry out instructions given by neural networks. So this is a neural network. We do not need to know how it works. All that matters is that when you look at it, it's a black box. This is what's inside the black box. But right now, this is essentially a box with information. And this information is sent over here, and this carries out those instructions. Now, the problem with most modern mobile devices is that they're so small, there's not enough hardware but the computing device is so small that a lot of the CPU and GPU essentially just isn't as powerful as a normal computer. So let's say you wanted to watch a high resolution video and play a demanding video game at the same time. Well, ultimately, one is going to suffer. One is going to degrade in performance. The goal of my project was to find a way to allow this video and video game to run with great performance. So replace the video game and the video with machine learning tasks. Instead of having two videos, you have two machine learning tasks. That is essentially what we used. And the goal is to find a way to increase the performance in both instead of just one. So find a way for both of them to have great performance equally without increasing power consumption. Because if you increase power consumption, ultimately your phone is going to die faster, and we don't want that. Now, that brings me to my methodology. So first off, we have the Odroid N2 board. This is obviously not a smartphone, but it is small enough to be considered a mobile device. And this is what we used. To the right, we have the high voltage power monitor. And so you can plug this into the wall, plug it into your computer, and use the software that is available with it, and then plug it into the Odroid, and you have the ability to measure power consumption, which is what you see over here. This is statistical results of what we're looking at. So the average power for a specific test we ran was 3.99 watts. And this board can run 12 volts without blowing it up, essentially, or burning it. So that's what you see here. It's set to 12 volts. Now the next tool we used is a Python API. And if you're not familiar with Python, it is a skill used, is a programming language used to, complete certain tasks, do certain things. And as far as API goes, it is a Python API means that it's a type of Python that was developed specifically for what we were needing to do. It was developed specifically for this device. So we could it had specific commands and whatnot that we could use for this. Now, what we did with this information is we were able to take this information and apply it to our Python API, which I will touch on a little bit later. So first off, the reason you have when you complete more than one task at the same time, the reason one suffers degradation while the other one has good performance is because normally all this information is sent directly to the GPU because it is bigger, it is more powerful. So the computer sends it to the GPU, essentially assuming that it can handle it when it can't. So let's say you have a soccer game going on, and one player's got the ball the whole time. Eventually, about halfway through the game, he's probably going to get tired and is going to suffer in performance. But if he passes that ball to his teammates can help him out, allow him to regain energy and work more efficiently, ultimately increasing performance in the whole team and winning the game. That's essentially what is happening here. So the goal of our project was to, or what we did was to take everything that's being sent to the GPU and split it using the Python API. We took some of it and shared it with this CPU and had some of it with the GPU. And to do this, we created, using the Python API, we created a partition right here. So we basically split the neural network and told some of it to go here and some of it to go here. Now what you see over here is a graph, of course, but this red line is considered the baseline. It starts at 1. So what this means, it's kind of like the control of the project. So this is what you would see if we didn't touch anything. We ran the tests and we didn't split it or anything. Everything's just being sent to the GPU. We get this red line. Now, the purple dots are the tests we ran. And in those tests, anything in the green above the red line is what went well, what performed well. So basically what worked, exceeded in performance, or I don't want to say exceeded, but what worked well. And the red is obviously the opposite. Now, that can bring me to my results. The yellow bar is the baseline, so as you can see it starts at 1, just like the control. And the oranger bar, the darker bar, which is our method, is the test that we ran. So we have mix 1 through 5 and then the average. And each mix is a test that we ran. Within each test, we ran 4 machine learning tasks concurrently at the same time. So think of it as like trying to play 4 videos at the same time or run 4 applications at the same time. We ran 4 machine learning tasks. So they're obviously not a video, but that is an analogy that I'm wanting to use to compare these. So we ran 4 in each, and as you can see, every test that we ran, it performed better than the baseline, where it was just going to the GPU. So I should touch back on this. Everything that was here, like the average power right here, we applied that to our Python API, and we're able to find a way to, we use the Python API, we use that tool to split everything, and keep power consumption from increasing too much. So that way the battery wouldn't die. So what we have here is like this test 1. It shows it did almost 3.6 times better than the baseline, and everything else here. So almost 2 times, 1 point. It's just going all the way. And the average, using our method with the Python API, we were able to get just over 2 times better. So this graph essentially shows that everything we're doing is working. We're able to increase performance while running multiple tasks concurrently without increasing power consumption so much. Some of them might have ran about maybe 10% like more power, but it's not enough to make too much of a noticeable difference. Now, these are like pictures of the tools we have. So this is just a screenshot of the software that I used, and this is an idea of like the Python API. And what we did is I put these here to show that for my future work I would like to use these tools and maybe some other tools that come across my way to increase or not increase, but improve these tests. Ultimately find a way to reduce power consumption even more and increase performance even more in the long run. So I can use these skills that I've learned as long as others to keep moving with the same project. Down here is my GitHub link. If you're not familiar with GitHub, it is basically a LinkedIn for programmers. So I have an account on there. You can go there and you can see the scripts that I wrote using Python and whatnot, and you can just see the work that other people do if it's public. So that's what that is. And then of course we have my references. And then I would like to thank the SI Bridges program as well as Dr. Anagnostopoulos and the graduate student Andreas for helping me with the project. I'd also like to thank NIH for funding the research as well as the engineering department. With that being said, that is the end of my speech.